After studying this module, you shall be able to know how distortion alters the absorption spectra of the complexes. Also, you will learn about the hole formation in the complexes. You can identify the reasons responsible for the anomalous absorption spectrum of the various complexes. You can also evaluate the reason behind the Jane-Taylor distortion in the complexes. Introduction. The absorption of the UV visible light by the octahedral coordination complexes leads to the transfer of d electrons from the lower T2G level to the upper EG level of the d orbital. This transfer, known as dt transition, is the reason behind the origin of UV visible absorption spectrum of the complexes. Accordingly, the absorption behavior of these complexes is studied with the help of various correlation diagrams, and hence the number of absorption bands depending upon the total number of d electrons in the orbital. In most of the cases, the number of band is in accordance with the theoretically predicted numbers, but in some cases, inconsistency is observed. One such example is the Jane-Taylor distortion. In addition, it has also been observed that in general, tetrahedral complexes are more intensely colored in comparison to the octahedral one. This is because of the lack of center of symmetry, which actually makes the transitions better allowed in nature.
Now we are going to discuss the effect of distortions on the spectra of the complexes. In this context, first of all, we have to discuss what is Jane-Taylor distortion. According to the Jane-Taylor distortion, if the ground electronic state of the nonlinear complex is orbitally degenerate, the complex will distort so as to remove the degeneracy and achieve a lower energy. In other words, it can also be said that there cannot be unequal occupation of the orbitals with identical energy, and if it is so, the molecule is going to distort itself to eliminate degeneracy. The Jane-Taylor effect only predicts that which of the structures will undergo distortion, but it cannot tell nature, extent of the distortion and the geometry of the distorted complex formed. In case of octahedral complexes, we have two sets of orbitals, e.g. which point directly at the approaching set of the ligands, and T2G which lie in between the axes and hence are not placed directly in the path of the ligands. Since EG orbitals are having greater interaction with the ligands, therefore Jane-Taylor effect is more pronounced in such cases. Examples include high spin D4, low spin D7 and D9 configurations. The distortion in case of octahedral complexes is also called tetragonal distortion. This has been shown in figure. Now consider a D4 or D9 electronic configuration. The octahedral geometry is degenerate since the last electron can occupy either of the two orbitals, the dx square y square or dz square in the EG level. Thus, Jane-Taylor distortion occurs in which the EG level splits into a dz square orbital and dx square y square orbital, and thus the degeneracy of the EG level is lost. As a result, reduction in energy happens or an increase in the CFSE value when the degeneracy is lost by the distortion. The tetragonal distortion may occur either by the elongation of the z-axis and compression of the x and y-axis, or by the compression of the z-axis and elongation of the x and y-axis. The Jane-Taylor effect cannot say which of these will occur, as it will vary from compound to compound. Both type of distortions are represented in figure. Now consider a D9 case where the last electron has to occupy the Eg set of orbitals lying higher in energy. With the occupation, the electron has a choice to occupy either a dx square y square or a dz square orbital, since both of them are degenerate in terms of energy. If the electron goes into the dz square orbital, the orbital interaction of the electron with the approaching ligands will lead to lowering in the energy of dz square orbital, and thus it will result in the tetragonal elongation in which the z-axis is elongated. This happens because the presence of an extra electron in the dz square orbital, which repels the incoming ligands along the z-axis to a greater extent in comparison to x and y axis. As a result of this repulsion, the z-axis is elongated in comparison to x and y. In contrast, if the last electron takes up the x square y square orbital, the orbital interaction will lead to lowering in energy of the dx square y square orbital. The dxy axes are elongated and z-axis will be compressed. Such a distortion is named as tetragonal compression. The T2G orbitals are also affected in the distortion, but since they are lying in between the axes of the incoming ligands, the extent of distortion is less. For a tetragonal elongation case, the orbitals of T2G having Z component will go down in energy, whereas in compression, the components having the X and Y component will be lower in energy. This has been depicted in figure. If the tetragonal distortion is fluxional, that is, the extended axis in the tetragonal distortion changes with time, but the time scale of existence of one fluxional form before it is transformed to another is shorter than the time scale of measurement, they only have an average structure which will be observed. When elongation along each of the axes is equally favorable, as in the case of copper 2 plus complex having H2O as the ligand, where all the ligands are same, then the observed average geometry is the octahedral geometry. This fluxional variation of distortion from one orientation to another is known as dynamic Jahn-Teller effect. Next, we are going to discuss the absorption spectra of the complexes with D1 and D9 electronic configuration. For D1 electronic configuration, the number of electron is 1, and thus the Tanabe-Sugano diagram is quite simple to be drawn and interpret. The configuration can be represented as T2G1 EgV0. Now, the excitation of the electron from the lower T2G level to the upper Eg level forms the excited state. The spin multiplicity of the ground and the excited state is same, and hence the transition from the ground to the excited state is spin allowed. The examples of D1 configuration include the titanium 3 plus complex with H2O as the ligand and chromium 2 plus complex with H2O as the ligand, etc. The Tanabe-Sugano diagram along with the absorption spectrum has been represented in figure. From the figure, it can be seen that only one transition is possible from the ground doublet T2G state to the excited doublet Eg state. Thus, only one transition band should be observed corresponding to the value of delta naught. But in actual practice, a single absorption band is split up into two features that can be seen from the absorption spectrum. This occurs because of the Jahn-Teller distortion, which leads to the splitting of a single band into two owing to the transition from a lower T2G level to the upper Eg level in the form of either dz square or dx square y square orbital. A similar effect of the Jahn-Teller distortion can be seen in case of the complexes with D9 electronic configuration, which shows the effect caused by distortion on the d orbitals due to change of the symmetry from octahedral to D4H. The decrease in symmetry is the result of the splitting of d orbitals due to their irregular occupancy. The doublet d term for the D9 configuration is split up into two states. The lower energy state is doublet E and the higher one is doublet T, which get further split up into singlet and doublet states under the effect of D4H field. A single absorption band in case of octahedral symmetry is further split up into two when the symmetry alters to D4H. This has been shown in figure which shows the Tanabe-Sugano diagram in the absorption spectrum for the D9 configuration. Next, we are going to discuss the tetrahedral complexes. In a tetrahedral ligand field, the ligands are situated at the opposite corners of a cube which circumscribes the octahedron. Hence, the orbitals which were directed between the ligands in the octahedral orientation are now directed toward the ligands in the tetrahedral orientation. Similarly, those orbitals which were directed towards the ligands in the octahedral orientation are now directed between the ligands in the tetrahedral orientation. In general, it has been seen that the tetrahedral complexes are more intensely colored as compared to the octahedral complexes. This actually results from the Laporte selection rule, which states that in case of molecules which are having a center of symmetry, the transitions within the same subshell are forbidden. In that case, it can be said that PP or DD transitions are Laporte forbidden. For any transition to take place, the change in the value of total orbital angular momentum between the final and the initial state should be delta L should be equal to plus minus 1, where delta L is equal to LF, that is the total angular momentum of the final state, subtracted Li, which is the total angular momentum of the initial state. The transitions which are between the state of same parity are disallowed, which means the d orbitals which are g-rate in terms of parity or symmetric with respect to the center of inversion cannot have transitions from one d orbital to the other. Also, p orbitals are ungirate, that is asymmetric with respect to the center of inversion, and thus transitions can take place within d and p orbitals. In very simple words, dd transitions as well as pp transitions are not allowed, whereas d to p and p to d are allowed. In case of tetrahedral complexes, the situation is opposite, since they do not possess center of symmetry and thus the transitions occurring are not from the Laporte forbidden rule. Because of such a fact, these transitions are intense in color in comparison to the octahedral complexes. The d orbitals for such tetrahedral complexes are split in the opposite style in comparison to octahedral one. This has been represented in figure which shows the splitting orbital diagram for octahedral and tetrahedral complexes. Considering the symmetry parameters, it can be concluded that D1 configuration of an octahedral field is analogous to the D9 case of the tetrahedral ligand field. Such a situation is depicted in the figure 6, where D1 electron in octahedral field occupies one of the triply degenerate T2G set, and on the other hand, in the case of D9 tetrahedral field, a hole is occupying the triply degenerate T2G set. In more practical terms, it can be said that for tetrahedral complexes with Dn configuration, the correlation diagrams for the octahedral complexes with D10-N can be used. Hence, for example, we can use a D7 correlation diagram of octahedral case for D3 tetrahedral case. This can be quite useful in predicting the spin allowed energy states with allowed transition in case of tetrahedral complexes.
Summary. The absorption behavior of the metal complexes is studied with the help of various correlation diagrams which determines the possible transitions and hence the number of absorption bands depending upon the total number of d electrons in the orbital. It has been observed that in general the tetrahedral complexes are more intensely colored in comparison to the octahedral one. This is due to the lack of center of symmetry which actually makes the transitions more allowed in nature. According to the Jane-Taylor distortion, if the ground electronic state of a non-linear complex is orbitally degenerate, the complex is going to distort itself to remove the degeneracy and hence achieve the lower energy. The Jane-Taylor distortion in case of D1 electronic configuration leads to the splitting of a single band into two owing to the transition from the lower T2G level to the upper EG level having either dz square or dx square y square orbital. In case of D9 complexes, effect is caused by the distortion of the d orbitals due to the change of the symmetry from octahedral to D4H in nature. The decrease in symmetry is the result of the splitting of the d orbitals due to their irregular occupancy. In a tetrahedral field, ligands are sited at opposite corners of a cube which circumscribes the octahedron. Hence, the orbitals which are directed between the ligands in the octahedral orientation are now directed toward the ligands in the tetrahedral orientation. Lippard's selection rule states that in the case of molecules which are having center of symmetry, the transition within the same subshell are forbidden. In that case, it can be said that PP or DD transitions are forbidden. In case of tetrahedral complexes, they do not possess center of symmetry and thus the transitions occurring are not Lippard forbidden, and as a consequence transitions are intense in color in comparison to the octahedral complexes. Importantly, for tetrahedral complexes with Dn configuration, the correlation diagrams for the octahedral complexes with D10-N can be used. For example, D1 configuration of the octahedral field is analogous to the D9 case of the tetrahedral field.